Hello, this is Dr. DA, and it's my pleasure to bring us into this new unit. This is our introduction to organic chemistry. We're going to start with a little review about the chemistry of carbon. Organic chemistry is the study of the compounds of carbon. Carbon, of course, is found here on the periodic table. It is atomic number 6. Which means a total of 6 protons, 6 electrons in its neutral state. It belongs to what we call group 4A, which means that there are 4 valence electrons available for bonding in carbon. It's a small atom with low electronegativity, and because of those features, it can form up to 4 covalent bonds. Electron configuration is 1s2, 2s2, 2p2, which means that those 4 electrons in the valence shell can be used to form hybrid orbitals, which allows carbon to have a great versatility in terms of bonding schemes. Also, very stable bonding allows the formation of very long carbon-carbon chains, which we call sometimes polymers. In terms of bonding, carbon can form single bonds, it can form double bonds, it can form triple bonds, as shown here. Single bonds are used by the formation of sp3 hybridization or sp3 hybrid orbitals. Double bonds with an accompanying set of 2 single bonds can be formed by sp2 hybridization. And a triple bond can be achieved by forming a linear structure using sp hybridization. In the next table, we can see how all these combine together to give us the different shapes of molecules built with carbon. On the left, we have the sp3 hybridization that gives us a standard tetrahedral shape, AX4, where A represents the central atom. X4 represents that there are 4 covalently bonded electron groups, such as the structure you see there at the bottom. In the next one, we see sp2 hybridization. In this case, you have a covalent bond that is double and then 2 single bonds. It gives us the trigonal planar shape, AX3. There are 2 types of linear arrangements we can have. Both of them use the sp hybridization and AX2 format. Again, A being the central atom, X being the bonded atoms. In the first one, we can see the carbon forming 2 double bonds, one on each side. In the second one, we can see it forming a triple bond on one side and a single bond on the other one. Keeping these things in mind, let's go ahead and consider some of the classifications of compounds that we have here. By the way, sometimes in some of these structures, you're going to see this R, this capital R, and that is a way of organic chemists indicating a group of atoms attached to the carbon, meaning that at that point, that group of atoms, whatever it is not of major interest. They want to draw our attention to the region that is, described completely. In this case, the 2 double bonds around that carbon. Let's start out with the hydrocarbons. These are compounds that contain just hydrogen and carbon atoms. And of course, we're familiar with hydrocarbons because they are the source of many of the so-called fossil fuels that we use in our society. We can subclassify the hydrocarbons into saturated and unsaturated, and we will get a bit of a better definition of these later on. This is based on a chemical property representing the ability of the compound to react with extra hydrogen. Saturated hydrocarbons consist of alkanes and cycloalkanes, and their main characteristic is that they only have single carbon-carbon bonds. There are no double or triple carbon-carbon bonds. Unsaturated hydrocarbons, on the other hand, consist of alkenes and alkynes. Alkenes are compounds that have at least 1 carbon-carbon double bond, and alkynes are compounds that have at least 1 carbon-carbon triple bond. There is a third category that really cannot fit into these two, and we call these the aromatic compounds. So we're going to start with the alkanes. We're going to go through some nomenclature and some structure of them. Then we'll go through the alkenes and alkynes, and then we will proceed to discuss other types of compounds of carbon that are not hydrocarbons. The general formula for an alkane is CnH2n plus 2. Remember, these are called saturated because each carbon essentially has the maximum number of bonds that it can have, the maximum number of single bonds it can have, whether it's to other carbon atoms or to hydrogen atoms. So let's build a table here using this formula for the first 5 values of n, 1, 2, 3, 4, 5. So for n equals 1, the formula would be CH4, and that compound is called methane. In organic chemistry, we don't use the nomenclature you learned in Chem 1A using the, what this would be essentially carbon tetrahydride. We don't use that type of nomenclature. Organic chemistry has been around for a long time, and they have their own methods of naming things, and we'll learn a few more nuances later on. For n equals 2, the formula is C2H6, and we call that compound ethane. For n equals 3, the compound is propane, has the formula C3H8. The next one will be C4H10, and that compound is called butane. The next one, C5H12, that one is called pentane. And if you continue the sequence here to 6, 7, 8, we start using the Greek prefixes that you were familiar with from Chem 1A. So 6 would be hexane, 7 would be heptane, 8 would be octane, 9 would be nonane, 10 would be decane, and then after that, we're not going to consider anything bigger than those compounds, all right? Now, it's very important that we look at the structures of the alkanes. So in the next video, I'm going to walk you through some of the simple structures and how do we represent them when we write them, let's say on a screen or a piece of paper.